being here after Marco wants. My name is Fernando. I'm also working at Percona, and I'm going to present a little bit of a different view of things, and that's about what is the overhead of running your database on Kubernetes. This is the kind of question that comes up when you are working on this and realizing that, you know, like Marco, many of us were not very into Kubernetes and databases for the reasons you might be thinking, and I will discuss some of them as well. But it's happening. Whether we like it or not, our customers are using it for real, right? So we were wondering, what is the overhead that it imposes, and in a particular context. So that's me. I joined Percona in the support team in 2013. More recently, I'm working in the consulting team with MySQL, Postgres, and Kubernetes as well. And the start of this is more and more from 2013 to now, we are seeing our customers all going to the cloud, right? And that's infrastructure as a service, that's where the databases are run. Now talking about database as a service, but more on-premise, right? So in the cloud, you have access to different kinds of machines, right? Instance sizes, a few CPU cores, and a little memory to pretty much more than that, right? And also different kinds of storage, right? You have not as much as IOPS as you want, but you have a granularity there, right? The standard disks you will get have this much IOPS and this much bandwidth, and you can purchase more, you can upgrade and everything. And considering that, you know, for most cloud providers nowadays, you can have access to all this hardware, both for your on-premise databases on EC2 or the compute engines or VMs, and you can also have all for the Kubernetes engine they offer to run Kubernetes, right? So considering this is true, that's the quick question that I was trying to figure out. If it's running on the same underlying hardware, both Kubernetes and on-premise, are we getting the same performance if we run exactly the same workloads on exactly the same kind of hardware? And that's what I was trying to figure out with this small project, right? So Kubernetes. Kubernetes is convenience, right? That's how I see it. You are trading some freedom of doing things your way by having things automated and kind of handled for you in different ways, right? So the virtualization has always been here, the automation as well. The orchestration differs a little bit from what we have with, you know, all the old puppets and CF engines and Terraform and Ansibles, right? In terms of resources, in general, we get CPU, memory, and the disk. But even though you can have local disks, and even though we know the local disks are much faster, we are trying mostly about the network attached storage for Kubernetes in this context. Because we are not, like in Kubernetes, in virtualization in general, we are not relying on exactly the same hardware. It might not be there tomorrow. Your storage needs to be, regardless of how it is redundant made, right? And if we think about a cluster, we are thinking about an ensemble of resources, a collection of resources. We have as many CPU, memory, and disk as we have in the machines that are part of this cluster, right? Let's forget about the disks. Let's just think about CPU and memory for now. That's the Kubernetes of the beginning, at least. So Kubernetes is for stateless workloads, right? And now so CPU and memory. And now, well, stateless workloads, but now we are more trustful of the underlying storage that it offers, right? So thinking about all this CPU and memory available in the Kubernetes cluster, our application runs with some CPU, it uses from this cluster, and some memory as well. And so we have several applications running our database cluster. And this, for us, was already a reason of concern because of how chaotic can be this environment, right? The database is something that we always try to protect and isolate somehow, right? And so this was like not what we intended to have. And the thing is, for the kind of going ahead of myself a little bit, but the application runs in a specific, even though you have all this collection of resources, we all know that the application will be running in one specific server, right? Not in half in one server and half in another server. But there is this migration that occurs for different reasons in Kubernetes. Some that you have control, some that you have not, and it's at the mercy of the cloud provider, right, that runs this. So what happens when you have a migration is that your application now starts running on a different server, but your storage will then be linked to that server, attached to that other server, and accessible from this other server. Right. Enters here the Kubernetes operators, which is, simplified very much, is, you know, we as DBAs know how MySQL works and what it needs. And we try to automate all these tasks according to the knowledge and behavior that we know how it works. And the Kubernetes were created precisely to help this automation be more consistent with what a DBA would do. Right? Facilitating the tasks of deployment, facilitating the deployment of a high available environment, and backups and restore, which, you know, this is one of my favorite features because it's always left for later, right? And when you deploy with an operator like the Percona one, that comes like first thing. Scaling both vertical and horizontally, and the integration with monitoring in the case of the Percona operator with PMM, right? Again, Kubernetes for me is a lot about convenience, because once you understand how it works and once you know how the operator works, you can have, it's no kidding, you can have a whole cluster build up from scratch in 5 minutes, provided that you already have the account with the cluster and everything, right? And that maybe is something that it's trivial, but at the same time, very, very convenient to have in a reproducible way. Right? When we were talking about the Percona operator for MySQL, and I am talking about the one based on PXC, the same one that Marco was presenting, which is, now we have the operator based on group replication as well, which went GA a couple of months ago. Haven't played enough with it, intend to do. But it's, again, a Kubernetes cluster for this operator starts with a 3-node cluster, right? Because PXC, by default, to start working with, it's a 3-node cluster. So we have also a 3-node Kubernetes cluster. Because we do not allow, and the operator makes sure that doesn't happen, you don't have 2 database nodes running on the same physical cluster, which would make no sense, right, for the high availability part. And so, the operator, if we simplify what it does, it deploys 3 data nodes in different servers with MySQL on each one of them, but also with AJ Proxy or Proxy SQL if you choose to use Proxy SQL. And these Proxy SQLs are configured to connect to any one of the nodes, right? There is no assigned writer node, even though in practice there is through the proxy itself, that you will always try and connect to the same one for writes. And there is different, the operator provides different access points. So you can have one just for writes, one just for reads that distributes the read traffic across them. This is all prepared for you. And then the application will rely on the cloud provider's load balancer to do things, to the connection, right? And the load balance is the one that is going to be distributing and routing the connection. Now, so we have the database running on each node on different physical server. But if we just have this Kubernetes cluster with 3 physical nodes, and we also want our application to run on the same Kubernetes cluster, it will be running in one of those nodes. And that's something that it's like this. But it's not something that we want to be in many times, right? We are trying to escape from the LAMP model. We are trying to have our database running as best as it can in the hardware that we are providing to it. So for many microservices, that's still the case. But this presentation is more thinking about something that is not a microservice, that is something that you would run on dedicated machines, right? So instead of having that, and that's something that's not super clear when you start working with Kubernetes, but you could have different node pools that are part of the same Kubernetes cluster. And that's what I'm doing with the tests I run for this presentation. So I have node pool A where I'm running my database and only my database, and I have node pool B where I'm running my application, which or the applications, right? Which in this case is Sysbench. It's like we are going to see next. So the testing itself, I am comparing 2 cloud providers. One of these then is AWS with the EKS Kubernetes engine, with EC2, which is the base reference. And the other cloud provider, I found out I cannot say what it is because of this, the license, right? So I'm calling it Cloud B. I've run 2 workloads. One of them is Sysbench OLTP, and the other one is Sysbench TPC-C. And I'm using 2 data sets. One that fits in memory, so mostly everything is in memory. The hot data is in memory. And the other one where it is not, right? So one is 10 times bigger than the other. And for the comparison, I'm running, so 4 machines, like I was saying, in EC2, and those machines are with 8 vCPUs and 32 gigabytes of memory. So very standard small machines, not the kind of one we were doing for the terabytes test, right? We are talking here about a 300 gigabyte database. And I'm doing the same with the Kubernetes engine and on EKS, right? PMM I set up on a different server on EC2 that was monitoring both environments. And for EC2 and for EKS, I'm using the same disk, which is standard GP3 data disk, 1 terabyte one. Okay, so all the constraints you should have for a GP3 1 terabyte size running on this kind of machine, it should be similar whether you're running it on EKS or EC2. And this is just a note on how we isolate things. So we use what we call Kubernetes annotations for this. So when I define on the Percona operator CR YAML file, which is the main configuration file, think about it as the my.cnf configuration file for MySQL, but this for the whole Kubernetes thing. I am setting up, configuring the affinity, which is how the clusters, where things can run in the cluster, in a way that I'm saying my PXC nodes, they should run in a node group that is called the default pool. That's the node pool of my database, right? And there is another rule here that says that we cannot have the same 2 data nodes running on the same physical machine. That's the standard. This is not. This you need to do it yourself. And when I set up, when I deploy the Sysbench container, I did so in a way that it was saying it needs to be run on the extra pool. That's the separate server on the separate node. And what this creates is this. I have 3 instances of AJ proxy and PXC, each pair of them running in different machines, right? And I have Sysbench running on the 4th one. And this is the high-level architecture of what the Kubernetes does. This is a Kubernetes node, and I have different pods running in this Kubernetes. Like if we take the yellow ones, for example, I have one AJ proxy here and one PXC data node here, and I could have the operator running here or in another one, which is a very small in terms of resources and everything. And each pod has different containers, right? So, but the essence of it is the PXC container, which is running MySQL. Then we have a separate one for logs and other things. In terms of configuration, very, very standard, simple things. It's still PXC 8.0, running the operator 1.18. That's the, if you just deploy the 1.18 operator from MySQL, from Percona, that's what you're going to get. You can configure a different version of MySQL that also works. And I'm running very, very standard things. I just set up the buffer pool, the redo log, and the Galera cache size, right? And Dimitri was commenting on his presentation this morning that, you know, the InnoDB dedicated server is all you need now, right? But so the first thing is this: if this is a 32 gigabytes server, why I'm just reserving 22 gigabytes of RAM for the InnoDB buffer pool, right? If it could be going higher, right? But what I found out when I was running Sysbench prepare was that on Kubernetes, the out-of-memory monitor, not from Linux, but from Kubernetes, was killing my data pod, right? So that's already something that, you know, to consider. So instead of going 25 gigabytes, which I could go on bare metal, I had to go lower. And that's something I didn't investigate further to see what it is. It's on my to-do list.
What's your pod configuration? Like the server has 32 gigabyte of RAM, but your container in your pod, what is its memory allocation?
Unrestricted. Yeah, that's, if you remember me, Jean-Francois, it's the very last slide. I go back to that. Thank you. So Sysbench 1.0 is still the one without SSL. Now we have the 1.1 with SSL, but it was after I started the tests. So OLTP and TPC-C, right? There is the small data set and there is the big data set. Both of them with 8 tables for OLTP and 10 tables for TPC-C. The difference is the size of the tables, right, in each of these data sets. And this is just an example of running the OLTP read-write workload. And what I wanted to highlight here is that I am bypassing AJ proxy. So I set up AJ proxy. Well, the operator sets up AJ proxy for you. I have set up AJ proxy on EC2 to mimic the Kubernetes environment, but I decided to bypass it and write specifically to node 0, right? 64 threads. Didn't do a variation of the number of threads. I have 8 cores, so that's 4 threads per core, 1 hour runs. And TPC-C, same thing. Here I'm going straight to node 0, also 64 threads. How I'm doing that? And I will show you the sequence, then I will show you a graph where it will become much more clear what I'm doing. So I'm running prepare on OLTP, then I'm running the read-write workload once, and I'm running the read-only workload 3 times for the OLTP workload. Then I'm running TPC-C prepare and running the TPC-C workload 3 times. And then I'm repeating all this process again. So I have 2 samples. I will show you next. I have 4 samples for each round. This is the graph I wanted to show you, and it shows 1 full round of running the big and the small data set, right? So first I have the OLTP workload, then the TPC-C, and then again for the small data set, OLTP and TPC-C. And this first part here is the prepare. Then I have the read-write workload, which I only run once, and we were not seeing it in the graphs, because what I decided to do was I'm using the OLTP workload as my benchmark for read-only workloads. So that's when I'm running it 3 times. And then for TPC-C, I'm running it also 3 times, the read-write. And again, the same thing for the small data set. Right? This one was for EKS. It's representative of EKS. Now, just notice this, that really after I run the read-write workload for OLTP, I have still some payload from the checkpoint system here for this first read-only sample, right? So I am discarding the first read-only sample. I'm only considering the second and third of each of them. And just for a visualization, this first one for EKS, and the second one was for the database on EC2. And we immediately already see some differences here, but we will get to that. And this is just to show more or less the anatomy of the workload, even though we'll talk about another example. This is for the, we can see in terms of buffer pool requests that one is fetching a lot of pages from the disk and the big data set, right? No matter what, it doesn't fit in memory. And the small data set, which is to the right here, much less going to disk and much more based on the data in memory. And so for the data disk, just accelerate a little bit. This, on EKS, this data disk for GP3 is limited to 3,000 IOPS. And we see that happening here and here for the read-only workloads, not so much for the other ones. And again, that's, you will see that no matter where you run them, right? In terms of disk writes, we have a huge effect of Galera, like Marco was showing in his presentation. So there's flow control, right? And what that means, you will never get the same write throughput you would get from a regular asynchronous MySQL replication or a standalone server. That's what it is, right? Part of the high availability cost. But that's the same. What I wanted to emphasize here is that the same. What you have on EC2 is what you have on EKS as well. And this slide was more for comparison what each workload does, right? But I won't go into details. In terms of questions, of course, the OLTP is much more short queries, and you'll get very much higher transaction per second count or query per second count than the TPC-C one. Going to the results, and I have just 5 minutes. Again, this is the graph. Again, taking only the second and third of each one of the rounds. So 2 rounds for big, 2 rounds for small. And this is the first one for AWS read-only big data set. So we have the workload running on EC2 is slightly higher than the one that is running on EKS. When it comes to TPC-C and the big data set, we have a much closer alignment here. Again, the workloads are very different. For the small data set and read-only, more or less the same thing. Not as many query per second, but close to the big data set. Now, this is the shocking part here. When I'm running the TPC-C small, I am getting half as much query per second than I am getting on EC2. So blue line is EKS, Kubernetes, red line is EC2 for AWS. Right. Right, but hold your thought. And this is a general view of the workload. So again, the only one that really kind of stands out is this one here and this one, which is twice as much for the same hardware. This is Cloud B, much closer in the 3 workloads, but the exact same rate for the TPC-C small data set. Exact same thing. This is Cloud B, again, a full view, and this is AWS. And we look at the round numbers. When we compare EKS and EC2, so I'm taking the on-premise or EC2 or the virtual machines for the Cloud B as the reference and using the Kubernetes results based on that, right? We get very close on everything, but the TPC-C is small data set. So data set that fits in memory is the one where we are getting half the performance on Kubernetes. And that, see, first thing I'm looking at CPU use. Look, 40% here, 80% here translates directly to 20,000 query per second here and 40,000 query per second here. That's on the Cloud B instance. If we look at the EKS and EC2, not as much difference in terms of CPU usage, close by, very close by, in fact, right?
Well, no, it's 20%, 40%.
Yeah, yeah, you're right.
Double.
Same thing. And double here as well. That's something we do not see when we are talking about the big data set, which is, again, very similar. This was Cloud B here, and AWS here. No, I wasn't limiting the resources for the data containers at all, which means, yes, I'm starting with a minimal requests, but I'm not putting a hard limit on that, which means Kubernetes is free, the data containers are free to use as many resources as they want. And I also try, after run all these tests, to, you know what, I'm just going to remove the requests just in case. And I got the exact same results. So next steps for me is look into this TPC-C small data set with Chetan, which is our Kubernetes expert. I'm taking this all to the Percona, in fact, to discuss. And I also want to look at the group replication, how that is different. Starting doing that with Postgres as well, but didn't complete that. And it's something maybe to show a case in Percona Live.